Good evening. We are now starting the third session. I have already uploaded session 1 and session 2 of chapter 1, electric charges and fields. I hope all of you have gone through the two sessions in which we discussed a chapter starting with basic properties of electric charges. Then we went on to Coulomb's law. Then we went on to electric field lines and electric flux. Then I think in session 2 we dealt with electric dipole moment, and the electric field along the axis of an electric dipole. Today we are going into the next derivation of that electric dipole, which is finding out the electric field along the equatorial point or equatorial axis. Remember, this is plus q and minus q separated by a distance 2a, and that is what you call as a dipole. And for a dipole, the net charge is always 0, because whenever there is a plus q, there is always a minus q. So naturally, the net charge will be 0. And this line joining the two charges is what you call as the axis. If I extend this line to the left or to the right, they are all axial points. So what we did in the last class is, we extended the line to the right, marked a point P which is at a distance x from the center, and we call that point P as an axial point. And we derived the equation for the electric field at the axial point. Magnitude was given by 1 by 4 pi epsilon 0, 2p by x cube, x being the distance from the center to point P. Its direction was the same as that of the dipole moment. Dipole moment is always directed from the negative q to the positive q. So E axial is also in the same direction, negative q to positive q. I hope you remember what dipole moment is. Dipole moment is defined as the product of any one of the charges multiplied by the total distance between the two charges, 2a. It's a vector quantity directed from negative q to positive q. Its SI unit is Coulomb meter. Let me first tell you what an equatorial point is. See, if this is your dipole, plus q and minus q separated by a distance 2a, and if you have a line which is passing through the center but perpendicular to the axis, such a line is what you call as the equatorial line. So if you look at my diagram here, we have the plus q and the minus q. From here to here, this is the center of the dipole. So this is A, this is another A. Then I have taken an equatorial axis, meaning a line, this dotted line passing through the center and perpendicular to the axis is what you call as the equatorial line. I have taken a point P, which is the equatorial point, which is at a distance x from the center of the dipole. And we are now going to find out the electric field at point P. Naturally, there will be two electric fields because each of these will behave as a source charge. Now, if you take plus q as a source charge, you already know that all positive charges have electric fields radially away from the source charge, because to find the electric field, what we normally do is, imagine there is a plus 1 coulomb here. Force experienced by that plus 1 coulomb is what you call as electric field. So this plus q, which is a source charge, will repel the plus 1 coulomb, and so we have a radial field away from the source charge. That's why E plus q is marked like this. If you are taking minus q as a source charge, this minus q will attract the plus 1 coulomb, and that is why this is radially inwards. This electric field E due to minus q will be radially inward towards the minus q. So now at point P, we have two fields, one E plus q and the other is E minus q. In class 11, we learned vector addition. If there are two vectors in the same straight line, we will simply add the two, and the direction of the resultant vector will be the same as the ones that you added. If you have two vectors in opposite direction but they are in the same straight line, then you simply subtract. The resultant vector will be in the direction of the larger one. But here you see, you have two vectors which are not in the same straight line. So you can add it using parallelogram law of vector addition, where these two vectors will become the adjacent sides of a parallelogram, and to complete the parallelogram, the diagonal will give you the resultant. Or there's another way of adding it. You can resolve this E plus Q into two components, E minus Q also into two components, then add the horizontal component and add the vertical components. I hope you remember resolving that too. We have done in class 11. When you resolve a vector, the adjacent side will be the cos theta term and the opposite side will be the sin theta term. So now I am going to resolve E plus Q into two components. E plus Q here, see now let me first show you that this is an isosceles triangle. Here you have A and this is X. So if you use Pythagoras, this side will be root of A square plus X square using Pythagoras. Similarly, for this side also, this is A and this is X. So this side also is going to be root of A square plus X square. So you will see this triangle, these two sides have the same length. So they are isosceles triangles, so that their base angles will be the same. Here it will be theta, here also it will be theta. Now if I draw a line parallel like this, a line parallel to this, these two lines are parallel but transversal. So if this is theta, this is also going to be theta because they are corresponding angles. Similarly, if this is theta, this will also be theta because these two form alternate angles. So because this and this are same, corresponding, and this is also equal to this because they are alternate angles. Now we will do the resolving. Now E plus Q will have two components. One is the adjacent component, the other is the opposite component. Here this horizontal component or adjacent component will be the cos theta term. So this will be E plus Q cos theta, and here you will have the other component E plus Q sin theta. Similarly, this E minus Q also I can resolve into two components. This is the adjacent side. So here I will have E minus Q cos theta, and here I will have E minus Q sin theta. I hope you understood this. That is, E plus Q has a component E plus Q cos theta, E plus Q sin theta. Similarly, E minus Q here has a component E minus Q cos theta, E minus Q sin theta. Let us now write the equation for E plus Q and E minus Q. E plus Q, do you remember the formula for magnitude of an electric field? 1 by 4 pi epsilon 0 Q by R square, where Q is the source charge, R is the distance from the source charge to the point P where you are finding the electric field. So here it will be 1 by 4 pi epsilon 0. Your source charge, this is plus Q, Q by distance from the source charge to point P, that is this distance, is root of A square plus X square. The whole square will be A square plus X square. Similarly, E minus Q will be 1 by 4 pi epsilon 0. You have a minus Q here, the source charge. So Q by, you will see that this distance from the source charge to the point P, this distance is also root of A square plus X square. The whole square you will have A square plus X square. I did not include the negative sign here because in vector addition, we only need the magnitudes to add. We write down the magnitudes. If they are in the same straight line, you add them. If they are opposite in direction, you subtract them. If they form the sides of a parallelogram, you can use parallelogram law of vector addition or resolving. So whether you add or subtract or not depends on the direction. Here we need only the magnitude. So now the net electric field, that is E equatorial, will be, see, look at the point P, there is an E plus Q sin theta and a E minus Q sin theta. Here plus Q sin, E plus Q is this much, E minus Q is also the same, both are same. So in magnitude, E plus Q and E minus Q are same. Similarly, these two theta is also the same. So E plus Q sin theta and E minus Q sin theta are equal in direction but opposite in direction, are equal in magnitude but opposite in direction. So they will simply cancel each other. But you will see E minus Q cos theta and E plus Q cos theta both are in the same direction. So we will add the two, E plus Q cos theta and E minus Q cos theta, same magnitude. So I may simply write 2 into E plus Q cos theta. Now I am going to substitute 2 into E plus Q or minus Q, both have the same magnitude, Q by A square plus X square into cos theta here will be, this is the adjacent side, this is A. So this is the adjacent side, this is the hypotenuse. Cos theta is adjacent side by hypotenuse. So A by A square plus X square the whole raised to 1 by 2, because square root I can write as 1 by 2. Now this is going to be equal to, remember this 2q into A is dipole moment, because what is dipole moment? Any one charge into total distance 2A. So I may replace it as 1 by 4 pi epsilon 0. 2qa is what you have as dipole moment by A square plus X square the whole raised to, there is a 1 here and a 1 by 2 here, 1.5, which is 3 by 2. So we have 3 by 2, and this is your equation for E equatorial. So E equatorial is 1 by 4 pi epsilon 0 P by A square plus X square the whole raised to 3 by 2. Now like the last derivation, we will take the special case here. Special case is when this distance X is much larger than this A. Suppose your point P is very far away from the dipole, then X is much greater than A. So we will take the special case. The special case is when X is much larger than A. In this formula I can neglect the A, so that this A is gone. X square is to 3 by 2, 2 and 2 will get cancelled. You will simply have an X cube. So we have E equatorial equal to 1 by 4 pi epsilon 0 P by X cube. This is your final formula. Okay. Now here P is a dipole moment, which is a vector. E equatorial is also a vector. Let us check if they have the same direction. See, this E plus Q and E minus Q sin theta got cancelled. So the net field is only E plus Q cos theta and E minus Q cos theta, both in the same direction. So resultant vector also has to be in the same direction, that is to the right. So it is from plus Q to minus Q to the right. But dipole moment, you know, is always directed from negative Q to positive Q. So it is to the left. So in this case, E equatorial and dipole moment are in opposite directions. So I will put a negative sign showing you that dipole moment always directed from negative to positive, but E equatorial will always be directed from positive Q to minus Q. Now another thing that you should note here is, if you compare the magnitude with E axial, you will see E axial there was a 2P by X cube. So you will see that E axial is always twice E equatorial, but E axial and E equatorial are exactly opposite in direction, because E axial has same direction as dipole moment to the left here, but E equatorial is to the right. So E axial and E equatorial are exactly opposite to each other, having an angle of 180 degree between them. So this is what we have as E equatorial for electric dipole. After this, we are going to go into the third derivation on electric dipole, that is torque acting on the electric dipole. That is there on your page 5 of the printed note, 5 and 6 of your printed note. We have the next derivation, and that is what we are going to do now. Now I am going to take a external field. See, your electric dipole has two fields, has a field around it. We derived the expression for E axial and E equatorial. So that's over. Now what I am drawing here is an electric field. Suppose I keep a positive plate here and a negative plate here, then I have an electric field. I am keeping a uniform electric field. Equally spaced lines represent uniform electric fields to the right, because electric fields external, and if it is positive here and negative here, always external electric fields are directed from positive to negative. In this field, I am going to keep a dipole with the plus q here and the minus q here. So this total distance, which is 2a, is directed from negative q to positive q. Dipole moment P also in this direction, and E is here. Now this angle between the dipole moment and electric field I am keeping as theta. Now what will happen here is, this electric dipole, because you have a positive charge and a negative plate here, this negative plate will attract this positive charge with a force equal to Q times E from the first section. I hope you remember this formula. E is what? Force on unit charge. So if there is Q charge, the total force will be F equal to QE. Similarly, this minus Q here, you have a positive plate here. So this negative charge will be attracted towards the positive plate with the same force F equal to QE. Why? Because both the charges are anyway the same, and we have a uniform electric field. Uniform electric field means magnitude of the field is the same everywhere. So this force and this force are going to be the same. So now you will see, do you remember what such forces are called? Class 11, I told you, equal and opposite forces acting on a body is what you call as a couple. Now what a couple does is, it can never produce translational motion. Simply because translational motion means your dipole cannot move in the field like this. Translatory motion not possible, simply because there is a QE, there is another QE, but both are in opposite directions on the body. So net force on the body is 0. So the body cannot have translatory motion. But a couple produces torque, because equal and opposite forces will now rotate the dipole in the electric field. What we are now going to do is derive an expression for that torque. Last year I have already taught you that torque on any couple formula is given by any one of these forces, because anyway both the forces are the same, multiplied by the perpendicular distance between the two forces. The two forces means one force is here, the other force is here, perpendicular distance. This is not the perpendicular distance. So you will see, if I draw a dotted line like this, that is, I take this A and this as B, this is the perpendicular distance between the two forces. You see, we have one force here like this, and the other force here like this, and the perpendicular distance between them is this AB that we are talking about. Is that clear? So we have AB as a perpendicular distance, and that is what we want in the formula. Now if you take this triangle, look at sin theta is going to be equal to, sin theta will be opposite side, AB by the hypotenuse, that is 2A, and if I cross multiply like this AB, the perpendicular distance is going to be 2A into sin theta. That is what we want here. So now I am going to write torque equal to any one force. Both the forces have the same magnitude. So Q times E multiplied by perpendicular distance AB is 2A sin theta. So we have a 2A sin theta here. And as you know, Q into 2A is what? Dipole moment. So we have PE sin theta as the torque. Now P is a vector, E is also another vector, and theta is the angle between the P and the E, that is theta. So torque is going to be equal to, magnitude is PE sin theta. If you see sin theta, you must know it is a vector product. Cos theta means it is a dot product, scalar product, but sin theta is always a cross product, which is called the vector product. So which means this resultant is also going to be a vector. So we need to write torque vector is equal to P cross E, the cross product. Since it is a cross product, it has a magnitude given by PE sin theta. It will also have a direction given by last year, we learned it as right hand screw rule. That is, if you hold a screw in your right hand, when you turn the head of the screw in the direction of A to B, the direction in which the tip moves will be the direction of the resultant vector. Basically, I think I've explained it like this for you. If you have two vectors A and B taken like this, A and B, maintaining an angle theta between them, the cross product will always be perpendicular to the plane containing A and B. That means your resultant will be perpendicular to the plane. Perpendicular would mean either perpendicular and outwards like this, or perpendicular and inwards like this towards me, or perpendicular and outwards like this towards you. Whether it is out or in depends on whether how you turn it. That is, if you are taking A cross B, you will see you are turning in the anti-clockwise direction. Anti-clockwise direction would mean perpendicular and outwards towards you. If you are taking B cross A, then you are turning in the clockwise direction. That would be perpendicular and inwards. Okay. If your plane is like this, A cross B is anti-clockwise turn, outwards, upwards, or B cross A is clockwise, inwards or downwards. So that means your resultant vector C is always perpendicular to B and to A, because it has to be perpendicular to the plane containing A and B. So here we have toe will always be perpendicular to the plane containing P and E. If you look at the diagram here, this is P and this is E. So your torque is going to be perpendicular to the plane of the board, because P and E are in the plane of the board. Because when you turn from P to E, you are turning in the clockwise direction. Your torque is going to be perpendicular and inwards. Inwards meaning perpendicular to the plane of the board and inwards. I hope this much is clear to you. So whenever you keep your dipole in an external field, there will be no translatory motion because the net force is 0, but it will produce a torque that rotates the dipole in the field. The magnitude will be given by Pe sin theta. Direction will always be perpendicular to the plane containing P and E. And if you are turning from P to E in the clockwise direction, your resultant will be inwards. If you are turning from P to E in the anti-clockwise direction, your torque will be upwards, outwards and so on. Another thing I want you to note here is your torque definitely can have different values depending on how you place your dipole. For example, suppose your electric field is in this direction, okay? And then I am going to keep your dipole is going to be kept, minus Q is kept here, plus Q is kept here, so that your dipole moment is also in the same direction. Do you see now? P and E are in the same direction. Which case, sin 0 is 0, there will be no torque. So if your dipole is kept in such a manner that P and E are parallel to each other, it does not experience any torque. If you turn it, that is you keep plus Q here and minus Q here, so that your dipole moment is now like this, from minus Q to plus Q, so that angle between E and P is theta equal to 180 degree. Even then, sin 180 will be 0. But on the other hand, if you now keep your dipole like this, let's say here we keep a minus Q and here we keep the plus Q, so that your dipole moment is directed from minus Q to plus Q. Now P and E maintain an angle of 90 degree. P is sin 90. Sin 90 will be 1, and you will see that there is maximum torque acting on the dipole. So we have completed the derivations on dipole in this chapter. There are 3. One is E axial. The last class I did that. E axial equal to 1 by 4 pi epsilon 0 2p by x cube. Today we did the second one, E equatorial, 1 by 4 pi epsilon 0 p by x cube. And the last one, torque experienced by an electric dipole when you place it in an external field, tau equal to P cross E. I'll close the session now, and we have only one more topic left in this chapter, that is Gauss's law and 3 applications, which I'll do tomorrow. Thank you.